Picture this. You're standing on the observation deck of humanity's most advanced spacecraft, watching our sun shrink to just another point of light in an ocean of stars. Earth is long gone from view, nothing more than a pale blue memory fading into the cosmic dark. This isn't science fiction anymore. This is the question that keeps astronomers awake at night and drives engineers to push the boundaries of what's possible. Will humans ever leave the solar system? Right now, as you listen to this, there's a piece of human technology racing through interstellar space at over 38,000 miles per hour. Voyager 1 crossed into the space between stars back in 2012, carrying with it a golden record filled with the sounds and images of Earth. It's our first ambassador to the galaxy. But here's the thing that'll blow your mind. At its current speed, Voyager 1 would take over 70,000 years to reach the nearest star. 70,000 years. That's longer than modern humans have existed. So when people ask if we'll ever leave the solar system, they're not just asking about sending another robotic probe into the void. They're asking whether human beings, with our fragile bodies and finite lifespans, could ever make that journey. Whether we could survive the crushing distances, the deadly radiation, and the sheer impossibility of traveling between worlds that are separated by gulfs so vast they make the Pacific Ocean look like a puddle. But here's what makes this question absolutely fascinating. We're living at the exact moment in human history where this impossible dream is starting to look less impossible. The technologies being developed right now, the discoveries being made about potentially habitable worlds orbiting other stars, and the growing understanding of how to keep humans alive in the most hostile environment imaginable are all converging into something that might actually be achievable. I'm going to take you on a journey through the cutting edge of interstellar travel research. We'll explore the mind-bending physics of moving between star systems, the revolutionary propulsion technologies that could get us there, and the biological challenges of keeping humans alive for journeys that could last centuries. But first, let me show you just how insanely difficult this problem really is. The scale of interstellar space defies human comprehension. If Earth were a grain of sand on a beach in California, the nearest star would be another grain of sand somewhere in Japan. The empty space between them wouldn't just be an ocean. It would be a void so complete that you could fit millions of solar systems in the gap without them ever coming close to touching each other. Proxima Centauri, our nearest stellar neighbor, sits 4.2 light-years away. That means light itself, traveling at the ultimate speed limit of the universe, takes over 4 years to make the trip. Light doesn't get tired. It doesn't need food or water or protection from cosmic radiation. It just goes at 186,000 miles per second for 4 solid years. And that's to reach the closest possible destination. Now imagine trying to send humans on that journey using conventional rockets. The space shuttle, one of the fastest vehicles humans have ever built, had a top speed of about 17,500 miles per hour in orbit. At that speed, a trip to Proxima Centauri would take approximately 165,000 years. That's not a human journey. That's a geological epoch. Entire civilizations could rise and fall before the spacecraft arrived at its destination. But the problem isn't just distance. It's everything that comes with distance. The moment you leave the protective bubble of our solar system, you enter a realm where the laws of survival get rewritten in the most brutal ways possible. First, there's radiation. Earth sits inside a magnetic field that deflects most of the high-energy particles streaming through space. Once you leave that protection behind, cosmic rays start tearing through your body at the cellular level. These aren't the gentle rays of sunlight we're talking about. These are atomic bullets fired by exploding stars, moving so fast they can punch holes through DNA and trigger cancers that no amount of medical technology could prevent. Then there's the cold. Interstellar space maintains a temperature of about 2.7 degrees above absolute zero. That's negative 450 degrees Fahrenheit, cold enough to freeze solid any material we've ever invented. Your spacecraft would need to generate its own heat for potentially thousands of years without any possibility of refueling or repair. And speaking of fuel, that's where things get truly mind-boggling. Every ounce of material you want to accelerate to interstellar speeds requires energy. The faster you want to go, the more energy you need. And the relationship isn't linear, it's exponential. Doubling your speed requires 4 times the energy. Getting to even a fraction of light speed using conventional propulsion would require more fuel than exists on Earth. Chemical rockets, the technology that got us to the moon, become laughably inadequate for interstellar travel. The rocket equation, that fundamental law of spaceflight, tells us that to accelerate any significant payload to interstellar speeds, you'd need a fuel tank the size of a planet. And that's just to get started. You'd still need fuel to slow down at your destination, unless you're planning to zip past your target star system at thousands of miles per second. But here's where things start to get interesting. Engineers and physicists have been working on this problem for decades, and they've come up with some solutions that sound like they belong in science fiction, but are grounded in real, testable physics. Nuclear propulsion represents the first major leap beyond chemical rockets. Instead of burning fuel and oxygen to create thrust, nuclear rockets use the controlled energy of atomic reactions to heat propellant and expel it at much higher speeds. This gives you more bang for your buck, literally. Nuclear thermal propulsion could potentially cut interstellar journey times from hundreds of thousands of years down to tens of thousands of years. Still impossibly long by human standards, but a significant improvement. Even more exotic is nuclear pulse propulsion. This concept involves detonating nuclear explosives behind a heavily shielded spacecraft and riding the shockwaves like a surfer catching waves. It sounds insane, and it probably is, but the physics actually work. Project Orion, developed by scientists in the 1950s and 60s, showed that nuclear pulse propulsion could theoretically accelerate spacecraft to several percent of light speed. Imagine that for a moment. A spacecraft powered by controlled nuclear explosions, each blast pushing it faster and faster until it's racing through space at 30 million miles per hour. At those speeds, the journey to Proxima Centauri drops from geological timescales down to something approaching human lifespans. Maybe 150 years instead of 150,000 years. But nuclear propulsion, as revolutionary as it sounds, still falls short of what we really need for practical interstellar travel. To make the journey survivable for humans, we need to think even bigger. We need to harness forces that exist only in the realm of theoretical physics and cutting-edge engineering. Fusion ramjets represent one of the most elegant solutions to the interstellar fuel problem. Instead of carrying all your fuel with you, a ramjet would scoop up hydrogen atoms from the interstellar medium and use them as fuel for a fusion reactor. The spacecraft would literally eat space as it traveled, accelerating continuously until it reached a significant fraction of light speed. The concept is beautiful in its simplicity. Hydrogen is the most abundant element in the universe, and interstellar space, despite being nearly empty, still contains about 1 hydrogen atom per cubic centimeter. A ramjet with a magnetic scoop, hundreds of kilometers wide, could collect enough fuel to sustain fusion reactions that would accelerate the spacecraft to perhaps 10 or 15% of light speed. At those velocities, Proxima Centauri becomes reachable within a human lifetime. The 4.2 light-year journey would take perhaps 30 to 40 years instead of millennia. Suddenly, interstellar travel transforms from a multi-generational odyssey into something an individual human could actually experience. But fusion ramjets come with their own set of seemingly impossible engineering challenges. The magnetic scoop would need to be larger than Earth. The fusion reactor would need to operate flawlessly for decades in the most hostile environment imaginable, and the spacecraft would need to withstand the constant bombardment of interstellar particles hitting its hull at relativistic speeds. Even more speculative are concepts that push the boundaries of known physics. Antimatter propulsion could theoretically accelerate spacecraft to significant fractions of light speed by annihilating matter and antimatter to create pure energy. The efficiency is unmatched. Einstein's famous equation, E equals mc squared, tells us that converting just a few grams of matter into energy would provide enough power to accelerate a spacecraft to incredible speeds. The problem is creating and storing antimatter. Currently, humanity can produce antimatter only in microscopic quantities at particle accelerators, and it costs trillions of dollars per gram. Even if we solved the production problem, storing antimatter safely for decades or centuries presents challenges that make nuclear engineering look simple. Then there are the truly exotic concepts that blur the line between science and speculation. Solar sails use the pressure of light itself to accelerate spacecraft without any fuel at all. While conventional solar sails would be far too slow for interstellar travel, breakthrough concepts like laser propulsion could potentially accelerate tiny spacecraft to 20% of light speed. The idea involves building massive laser arrays on Earth or in space and using them to push ultra-lightweight spacecraft equipped with reflective sails. The spacecraft would need to be incredibly small, perhaps no larger than a smartphone, but they could reach nearby star systems in just 20 or 30 years. These wouldn't carry humans, but they could serve as robotic scouts, sending back our first close-up images of potentially habitable exoplanets. But sending tiny robotic scouts is one thing. Getting actual human beings to another star system is an entirely different challenge that makes rocket science look like kindergarten math. The human body wasn't designed for interstellar travel. We evolved on a planet with specific gravity, atmospheric pressure, and radiation protection that simply don't exist in the void between stars. Every biological system in your body depends on conditions that you'd leave behind the moment you departed Earth's orbit. Let's start with the most basic problem. How do you keep humans alive for journeys that could last decades or centuries? Your body is essentially a complex chemical factory that requires constant inputs and produces constant waste. On Earth, we take for granted the elaborate ecosystems that recycle our air, purify our water, and provide our foods. An interstellar spacecraft would need to replicate all of these systems with perfect reliability for potentially hundreds of years. Closed-loop life support systems represent one of the most critical technologies for long-duration spaceflight. Every breath you exhale, every drop of water you use, every bit of waste your body produces would need to be captured, processed, and recycled back into something usable. The International Space Station already does this on a small scale, but extending these systems to work flawlessly for centuries is an engineering challenge that makes building the pyramids look trivial. Then there's the psychological dimension that nobody talks about. Imagine being locked in a metal can with the same group of people for your entire adult life, knowing that you'll never see Earth again, never breathe unfiltered air, never feel rain on your face. The isolation would be absolute. No rescue missions would be possible. No new faces would ever appear. The psychological stresses of interstellar travel could drive people insane long before they reach their destination. But perhaps the most daunting challenge is what scientists call the generation ship problem. For most interstellar journey scenarios, the people who begin the voyage won't be the ones who complete it. The spacecraft would become a traveling world, carrying multiple generations of humans who are born, live, and die in the space between stars. Think about the implications of that for a moment. You'd have children who've never seen a planet, adults who know Earth only as a story their grandparents told them, and elderly people who've spent their entire lives staring at the same metal walls. How do you maintain human culture and purpose across generations when the original mission might seem increasingly abstract and meaningless to people who've never known any other existence? The engineering challenges multiply when you consider generational travel. The spacecraft would need to be enormous to support a viable human population. We're not talking about a cramped capsule like the Apollo missions. We're talking about a self-contained world, potentially kilometers across, with its own ecosystems, manufacturing capabilities, and social institutions. This massive ship would need to maintain structural integrity for centuries while traveling through environment that's actively trying to destroy it. Micrometeorites would constantly pepper the hull. Cosmic radiation would slowly degrade every material and electronic system. Metal fatigue would accumulate over decades of acceleration and deceleration. And there would be no space dock, no repair facility, no possibility of replacement parts beyond what the ship could manufacture itself. But here's where the story takes a fascinating turn. Some of the most brilliant minds in science and engineering think they've found solutions to these seemingly impossible problems. And the answers involve technologies that are just starting to emerge from the realm of science fiction into actual laboratories. Cryogenic suspension, or what popular culture calls suspended animation, could theoretically allow humans to sleep through most of an interstellar journey. Instead of maintaining a fully active crew for centuries, you could keep the travelers in a state of controlled hibernation, aging slowly or perhaps not at all during the voyage. Medical researchers are already experimenting with induced hypothermia for trauma patients, and some animals naturally hibernate for months at a time. The idea is seductive. Load a spacecraft with sleeping passengers, accelerate to interstellar cruise speed, then wake everyone up when you arrive at your destination. No generation ships, no decades of psychological isolation, no closed-loop life support systems running for centuries. Just a long nap followed by waking up at a new world. But the reality of cryogenic suspension involves challenges that make rocket propulsion look straightforward. Freezing human tissue causes ice crystals to form inside cells, essentially shredding them from the inside out. Current cryogenic preservation techniques can maintain tissue samples or even whole organs for limited periods, but nobody has ever successfully frozen and revived a complex organism like a human being. Even if we solved the technical problems of cryogenic preservation, we'd still face the challenge of maintaining the sleeping passengers for decades or centuries. The spacecraft would need automated systems capable of monitoring and caring for hundreds or thousands of hibernating humans without any possibility of human intervention. One malfunction, one system failure, one unexpected problem could doom the entire mission. Alternative approaches focus on genetic engineering and human enhancement technologies that could adapt our bodies for interstellar travel. Instead of trying to recreate Earth conditions inside a spacecraft, we could potentially modify humans to better survive in the space environment. Enhanced radiation resistance could protect against cosmic rays. Modified metabolism could reduce the need for food and oxygen. Altered psychology could help humans cope with isolation and confinement. Some researchers even speculate about more dramatic modifications that would allow humans to survive in low pressure or low temperature environments. These concepts push us into territory where the line between human and post-human becomes blurry. Would genetically modified space travelers still be recognizably human? Would they be able to interact normally with unmodified humans when they reach their destination? And who gets to decide what modifications are acceptable and what changes cross the line into creating an entirely new species? But perhaps the most intriguing solution to the human survival problem involves not sending humans at all, at least not in the traditional sense. Digital consciousness transfer, still highly speculative, but grounded in advancing neuroscience research, could theoretically allow human minds to be uploaded into computer systems that could survive interstellar travel far more easily than biological bodies. A digital human wouldn't need food, water, or protection from radiation. They wouldn't age or suffer from the psychological stresses of confinement. They could potentially remain conscious throughout the entire journey, experiencing every moment of the voyage between stars. And if their hardware failed, backup copies could ensure that no consciousness would be lost. The philosophical implications are staggering. Would a digital copy of your consciousness still be you? Would it have the same rights, the same identity, the same essential humanity as the biological original? And what would happen when digital humans arrived at their destination? Would they construct robotic bodies to interact with the physical world? Would they remain forever digital, existing in virtual realities that could be far more elaborate and satisfying than any physical environment? These questions don't have easy answers, but they're becoming increasingly relevant as our understanding of consciousness and computing power continues to advance at exponential rates. The more we dig into these possibilities, the more we realize that leaving the solar system isn't just an engineering problem. It's a fundamental question about what it means to be human and how far we're willing to push the boundaries of our own existence. But let's step back from the far future speculation and look at what's actually happening right now in laboratories and research facilities around the world. Because while we're debating the philosophy of digital consciousness, real scientists are building real technologies that could make interstellar travel possible within our lifetimes. The Breakthrough Starshot Initiative, announced in 2016, represents humanity's first serious attempt at the interstellar exploration. The concept is elegantly simple and terrifyingly ambitious. Instead of building massive spacecraft, they're developing tiny probes no bigger than postage stamps that could be accelerated to 20% of light speed using powerful laser arrays. Picture this: a fleet of thousands of these miniature spacecraft, each weighing just a few grams, equipped with cameras, sensors, and communication systems built using the same technology that powers your smartphone. They'd be equipped with ultra-lightweight sails made from materials so thin they're essentially two-dimensional. Ground-based lasers would focus their beams on these sails, accelerating the tiny probes to speeds that would make our fastest rockets look like they're standing still. At 20% of light speed, these robotic scouts could reach Proxima Centauri in just 20 years. They'd zip past the star system in a matter of hours, frantically taking pictures and measurements before continuing into deep space. But those few hours of data collection could revolutionize our understanding of the nearest potentially habitable world beyond our solar system. The technology required for Breakthrough Starshot pushes the limits of what's currently possible, but it doesn't require any revolutionary breakthroughs in physics. The lasers exist, though they'd need to be scaled up dramatically. The materials for the sails are being developed in nanotechnology labs. The miniature electronics are advancing with each generation of smartphones and computers. What makes Breakthrough Starshot particularly exciting is that it represents a stepping stone toward more ambitious interstellar missions. If we can send tiny robots to other star systems, we can start learning what's actually out there. We can identify the most promising targets for future human missions. We can test interstellar communication systems and develop the experience needed for more complex missions. But sending postage stamp-sized robots is still a far cry from sending humans. For that, we need to think bigger, and some of the most promising research is happening in areas that most people have never heard of. Nuclear pulse propulsion is experiencing a renaissance thanks to advances in materials, science, and computer modeling. The original Project Orion was abandoned in the 1960s, partly because the engineering challenges seemed insurmountable with available technology. But modern materials can withstand far higher temperatures and radiation levels than anything available to those early pioneers. New designs for nuclear pulse spacecraft look nothing like the crude shock absorber systems envisioned in the 1950s. Instead of riding explosions like a pogo stick, modern concepts use magnetic fields to channel nuclear energy more efficiently. The spacecraft would essentially surf on controlled nuclear detonations, using magnetic nozzles to direct the energy and achieve unprecedented levels of thrust. Computer simulations suggest that advanced nuclear pulse systems could accelerate multi-thousand-ton spacecraft to 10 or 15% of light speed. That's fast enough to reach Proxima Centauri in 30 to 40 years, turning interstellar travel from a multi-generational odyssey into something a single human crew could potentially survive. Even more promising is research into fusion propulsion systems that don't require nuclear explosives. Fusion rockets would use the same process that powers the sun, fusing hydrogen atoms together to release enormous amounts of energy. The exhaust velocity from a fusion rocket could be orders of magnitude higher than anything achievable with chemical propulsion. The challenge with fusion propulsion has always been creating controlled fusion reactions that produce more energy than they consume. But recent breakthroughs in fusion research suggest we might finally be approaching that goal. Experimental reactors are achieving fusion conditions for longer periods and with higher energy outputs than ever before. If we can make fusion work for power generation on Earth, adapting it for spacecraft propulsion becomes much more feasible. A fusion-powered spacecraft could potentially achieve 5 to 10% of light speed, making interstellar journeys possible within human lifetimes without requiring massive generation ships or exotic technologies. But propulsion is only half the equation. The other half involves creating closed ecosystems that can sustain human life for decades in the most hostile environment imaginable. NASA's research into closed-loop life support systems has advanced dramatically since the early days of space exploration. The International Space Station already recycles about 90% of its water and a significant portion of its oxygen. But these systems still require regular resupply missions and maintenance that wouldn't be possible on an interstellar voyage. The key breakthrough involves creating truly regenerative life support systems that can operate indefinitely without external inputs. This requires understanding ecosystems at a level of detail that we're only beginning to achieve. Every microbe, every chemical reaction, every energy transfer needs to be accounted for and maintained in perfect balance. Some of the most promising research involves engineered ecosystems that use genetically modified plants and bacteria to create perfectly balanced recycling systems. These biological machines could potentially process human waste, purify air and water, and even produce food with near-perfect efficiency. Unlike mechanical systems that wear out and break down, biological systems can actually repair and improve themselves over time. Advanced hydroponics and aeroponics systems are already producing food in space with remarkable efficiency, but the interstellar missions would require food production systems that could operate for decades without any external inputs. This means developing crops that can provide complete human nutrition while using minimal resources and producing no waste that can't be recycled. The psychological challenges of interstellar travel are driving equally innovative research. Virtual reality technology could potentially create environments so realistic that crew members could experience Earth-like conditions even while traveling through empty space. Advanced AI companions could provide social interaction and intellectual stimulation that could help prevent the isolation and madness that would otherwise make long-duration missions impossible. But perhaps the most exciting development involves research into human hibernation that goes far beyond simple cryogenic freezing. Scientists are studying animals that naturally hibernate for months at a time, trying to understand the biological mechanisms that allow them to survive in suspended animation without suffering tissue damage. Recent experiments with induced hypothermia in medical settings have shown that humans can survive in reduced metabolic states for limited periods. Extending this to months or years would require dramatic advances in our understanding of human physiology, but the basic mechanisms appear to be possible within known biological systems. Even more intriguing is research into synthetic biology that could potentially create hybrid biological mechanical systems specifically designed for space travel. These wouldn't be traditional humans enhanced with technology, but entirely new forms of life engineered from the ground up to thrive in space environments. Such beings might have redundant organ systems, enhanced radiation resistance, and metabolisms that could survive on minimal resources for extended periods. They could potentially reproduce and maintain their populations during long interstellar journeys, creating self-sustaining communities that could establish colonies on distant worlds. The ethical questions raised by these possibilities are staggering. Who decides what modifications are acceptable? How do we ensure that enhanced humans or synthetic beings retain their essential humanity? What happens when modified space travelers encounter unmodified humans, either on Earth or at their destinations? But these questions assume that leaving the solar system requires sending physical beings at all. The most radical possibility involves abandoning biological existence entirely in favor of digital consciousness that could travel between stars at the speed of light. Advanced artificial intelligence research is revealing new insights into the nature of consciousness and identity. If consciousness is ultimately a pattern of information processing, then it might be possible to transfer human minds into computer systems that could survive interstellar travel far more easily than biological bodies. A digital human wouldn't face any of the physical challenges that make interstellar travel so difficult. They wouldn't need food, water, or protection from radiation. They could remain conscious throughout the entire journey, experiencing every moment of the voyage between stars. And they could potentially be transmitted to distant star systems as radio signals, arriving at their destinations at light speed rather than requiring decades or centuries of travel time. The technology for digital consciousness transfer doesn't exist yet, but the fundamental research is advancing rapidly. Brain-computer interfaces are becoming more sophisticated every year. Artificial intelligence systems are developing increasingly human-like reasoning capabilities. And our understanding of how consciousness emerges from neural activity is improving dramatically. Some researchers predict that digital consciousness transfer could become possible within the next 50 to 100 years. If they're right, interstellar travel could transform from a generations-long ordeal into something as simple as sending an email to another star system. But even if digital consciousness proves impossible, or if we decide it's too far removed from traditional humanity to be acceptable, other paths to interstellar travel are opening up that seemed impossible just decades ago. The discovery of thousands of exoplanets orbiting other stars has revealed that potentially habitable worlds are far more common than anyone expected. Within just 20 light years of Earth, astronomers have identified dozens of planets that could potentially support human life. Some of these worlds might even be more habitable than Earth, with more stable climates, fewer natural disasters, and conditions that could support larger populations. This abundance of potential destinations makes interstellar travel more compelling than ever before. We're not just talking about sending explorers into the unknown anymore. We're talking about reaching specific worlds that could serve as new homes for human civilization. The technologies needed to reach these worlds are advancing on multiple fronts simultaneously. Propulsion systems are becoming more efficient and powerful. Life support systems are becoming more reliable and self-sufficient. Our understanding of human adaptation to space environments is improving with every mission to the International Space Station. Perhaps most importantly, the cost of space access is dropping dramatically thanks to reusable rockets and commercial space companies. What once required the resources of entire nations can now be accomplished by private companies and even wealthy individuals. This democratization of space access makes ambitious interstellar missions far more feasible than they were during the early days of space exploration. But the timeline for human interstellar travel remains frustratingly uncertain. Conservative estimates suggest it could take centuries to develop the necessary technologies. Optimistic projections think it could happen within the next 50 to 100 years. The reality probably lies somewhere in between, depending on how quickly we can solve the fundamental challenges of propulsion, life support, and human survival in interstellar space. What's certain is that the question is no longer whether humans will ever leave the solar system, but when and how we'll do it. The physics allows it. The technology is advancing toward making it possible, and the destinations are waiting for us, scattered among the stars like islands in an infinite ocean. The first humans to make that journey will be explorers in the truest sense of the word, venturing into a realm where no human has ever gone before. They'll be leaving behind everything familiar, everything safe, everything that connects them to the history of our species. But they'll also be taking the first steps toward ensuring that human consciousness and culture can survive beyond the death of our sun, beyond the end of our solar system, and potentially beyond the end of our galaxy itself. The mathematics of survival become even more staggering when you consider what happens after we actually reach another star system. Landing on an alien world presents challenges that make the journey itself look simple by comparison. Everything we take for granted about planetary environments could be completely different on an exoplanet orbiting another star. Gravity might be twice as strong as Earth's, making every step feel like you're carrying another person on your back. The atmospheric pressure could crush you instantly, or it might be so thin that your blood would literally boil. The chemistry of the soil could be toxic to Earth life, and the radiation environment might be lethal without constant protection. But here's what makes this challenge fascinating, rather than just terrifying. We're developing technologies right now that could allow humans to terraform entire worlds, reshaping alien environments to support Earth life. Atmospheric processors could gradually convert hostile atmospheres into breathable air. Genetic engineering could create Earth plants and animals capable of surviving in alien conditions. And advanced robotics could build entire cities and infrastructure systems before the first human colonists even arrive. The concept of sending robotic precursor missions is gaining serious attention from mission planners. Imagine launching fleets of construction robots decades before any human mission, giving them time to establish manufacturing facilities, extract resources, and build habitable environments on distant worlds. By the time human colonists arrive, they could find fully prepared settlements waiting for them, complete with breathable atmospheres and sustainable ecosystems. This approach solves one of the most daunting aspects of interstellar colonization. Instead of asking humans to survive in completely alien environments using only what they can carry with them, robotic precursors could literally reshape entire worlds to meet human needs. The technology for this kind of large-scale planetary engineering doesn't exist yet, but the fundamental principles are well understood. Advanced 3D printing and molecular manufacturing could allow robots to construct entire cities from raw materials found on alien worlds. Self-replicating machines could multiply exponentially, turning a small initial robotic population into massive industrial capabilities within decades. And artificial intelligence systems could coordinate these efforts with a level of precision and efficiency that no human organization could match. But perhaps the most intriguing possibility involves not just terraforming alien worlds, but fundamentally altering human biology to thrive in whatever environments we encounter. Instead of changing planets to suit humans, we could change humans to suit planets. Genetic modifications that seem impossible today might become routine within the next century. Enhanced lungs could extract oxygen from thin atmospheres. Modified skin could protect against radiation levels that would kill unmodified humans. Altered metabolism could allow survival on completely different food sources, or even allow humans to derive energy directly from sunlight like plants. Some researchers envision even more radical modifications that would allow humans to survive in environments that are completely hostile to Earth life. Humans adapted for high-pressure worlds could potentially live underwater or in dense atmospheric conditions. Humans modified for low gravity could develop the ability to fly using wing-like appendages. The possibilities are limited only by our understanding of biology and our willingness to push the boundaries of what it means to be human. These modifications raise profound questions about identity and continuity. Would genetically enhanced space colonists still be human in any meaningful sense? Would they be able to interbreed with Earth humans, or would they represent the beginning of entirely new species? And how would human society handle the emergence of populations that are fundamentally different from baseline humanity? But genetic modification is just one approach to adapting humans for interstellar colonization. Mechanical augmentation could potentially provide many of the same benefits without permanently altering human biology. Powered exoskeletons could allow humans to function in high-gravity environments. Advanced life support suits could provide protection from radiation and toxic atmospheres. Neural implants could enhance human intelligence and memory, making colonists more capable of solving the complex problems they'll face on alien worlds. The boundary between human and machine becomes increasingly blurred as these technologies advance. Colonists might spend most of their time in robotic bodies designed for specific environments, transferring their consciousness between different platforms as needed. They could potentially exist as pure information, inhabiting whatever physical form is most appropriate for their current tasks. This flexibility could be crucial for successful interstellar colonization. Different worlds will require different solutions, and colonists who can adapt their physical forms to match local conditions will have enormous advantages over those locked into biological bodies optimized for Earth environments. But all of these technological solutions assume that we can maintain human civilization and culture across the vast distances and timescales involved in interstellar expansion. The social and political challenges might be even more difficult than the technical ones. Consider the problem of maintaining communication between interstellar colonies. Even at light speed, messages between star systems would take years to transmit. A conversation between Earth and Proxima Centauri would involve 8-year delays between question and answer. Real-time coordination of activities across multiple star systems would be completely impossible. This communication delay would force interstellar colonies to develop independent governance systems and cultures. Over time, colonies separated by light years of distance and decades of communication delay would inevitably diverge from each other and from Earth. They might develop different languages, different political systems, different values and beliefs. The result could be a human diaspora scattered across dozens or hundreds of star systems, each developing its own unique civilization while maintaining only tenuous connections to the others. Some colonies might thrive and expand to colonize additional worlds. Others might fail catastrophically, leaving only ruins and radio silence as evidence of their existence. This fragmentation of human civilization presents both opportunities and dangers. Independent colonies would be free to experiment with different social and political systems, potentially developing solutions to problems that have plagued humanity throughout history. But they might also develop in ways that Earth humans would find disturbing or unacceptable. Some colonies might embrace authoritarian control systems that prioritize survival over individual freedom. Others might develop technologies or practices that Earth considers dangerous or immoral. And without any practical way to intervene across interstellar distances, Earth would be powerless to influence these developments. The economic implications of interstellar colonization are equally complex. Traditional economic systems based on trade and resource exchange break down when transportation costs become astronomical and delivery times stretch across decades. Interstellar colonies would need to be almost completely self-sufficient, capable of producing everything they need from local resources. This requirement for self-sufficiency could actually drive rapid technological development. Colonies that can't import manufactured goods from Earth would be forced to develop advanced manufacturing capabilities, using whatever materials are available locally. They might discover new technologies or techniques that give them advantages over Earth-based civilization. Over time, successful interstellar colonies might become technologically superior to Earth, developing capabilities that their parent civilization lacks. This could lead to a complete reversal of the traditional colonial relationship, with Earth becoming dependent on its former colonies for advanced technologies and resources. But the most profound changes might involve human consciousness and identity. Living on alien worlds under alien skies could fundamentally alter how humans think about themselves and their place in the universe. Colonists who grow up on worlds with different day-night cycles, different seasonal patterns, and completely different environments might develop psychological and cultural characteristics that are unrecognizably human from an Earth perspective. Multiple generations of life on alien worlds could produce humans who are literally alien themselves, adapted not just physically, but mentally and culturally to conditions that Earth humans can barely imagine. They might develop new forms of art, music, and literature inspired by alien landscapes. They might discover new philosophical and spiritual perspectives based on their unique experiences. The diversity of human experience could explode exponentially as colonies spread across worlds with radically different characteristics. Desert worlds might produce cultures focused on conservation and efficiency. Ocean worlds might develop civilizations based entirely on aquatic life. High-gravity worlds might create societies that are fundamentally different from anything possible on Earth. This diversification of human experience represents both the greatest promise and the greatest risk of interstellar colonization. The expansion of human consciousness and culture across multiple worlds could lead to unprecedented creativity and innovation, but it could also lead to the fragmentation of humanity into species or subspecies so different that they can no longer recognize each other as kin. Managing this transformation will require careful thought about what aspects of humanity are essential to preserve and what aspects can be allowed to change. We'll need to develop new concepts of identity and community that can span interstellar distances and accommodate radical diversity in human form and culture. The technologies that make interstellar travel possible will also enable forms of human enhancement and modification that go far beyond anything possible with current biology. The humans who eventually colonize other star systems might be as different from us as we are from our earliest ancestors. They might possess capabilities that seem magical by today's standards, while retaining enough of our essential humanity to still be recognizable as our descendants. But before any of these long-term scenarios can unfold, we need to solve the immediate practical problems of getting humans to other star systems alive and intact. And that's where some of the most exciting current research comes into play. Advanced propulsion concepts are moving from theoretical physics into actual laboratory testing. Breakthrough propulsion physics programs at NASA and other research institutions are investigating exotic possibilities, like manipulating space-time itself to enable faster than light travel. While these concepts remain highly speculative, they're based on legitimate interpretations of general relativity and quantum mechanics. The idea involves creating regions of curved space-time that could allow spacecraft to effectively travel faster than light without violating the cosmic speed limit. The spacecraft itself would never exceed light speed, but the space around it would be compressed in front and expanded behind, allowing it to cover vast distances in short periods of time. These concepts require forms of energy and matter that we can't currently produce, but they don't violate any known laws of physics. If we can ever learn to manipulate space-time directly, interstellar travel could become as routine as international air travel is today. Even more immediate possibilities involve using the infrastructure of the solar system itself to enable interstellar missions. Massive solar power collectors positioned near the sun could generate the enormous amounts of energy needed for advanced propulsion systems. Asteroid mining operations could provide the raw materials for building huge spacecraft without depleting Earth's resources. The industrialization of space could make interstellar missions economically feasible by spreading the costs across the entire solar system economy rather than requiring individual nations to fund them independently. A truly spacefaring civilization with access to the resources of thousands of asteroids and moons could afford to build interstellar spacecraft on scales that seem impossible today. Within the next century, humans might establish permanent bases throughout the solar system, from orbital habitats around Earth to mining stations in the asteroid belt to research outposts on the moons of Jupiter and Saturn. This expansion would provide the technological foundation and economic base needed to support interstellar missions. The psychological preparation for interstellar travel is already beginning in the most isolated places on Earth. Researchers are studying how humans cope with extreme isolation in Antarctica, underwater habitats, and simulated space missions that last for months or years. These studies are revealing both the limits of human psychological endurance and potential techniques for overcoming them. Virtual reality environments could provide interstellar travelers with unlimited variety in their surroundings, preventing the claustrophobia and monotony that would otherwise make long-duration missions unbearable. Advanced artificial intelligence could serve as companions and counselors, providing social interaction and emotional support throughout the journey. But perhaps the most important preparation involves developing the cultural and philosophical frameworks that will guide humanity as we expand beyond our home star system. We need to think carefully about what values and principles we want to carry with us to the stars and how we can maintain them across the vast distances and timescales involved in interstellar civilization. The expansion of humanity beyond the solar system represents the next great chapter in our species' story. It's a chapter that could begin within the lifetimes of people alive today, depending on how quickly we can develop the necessary technologies and overcome the remaining challenges. The question isn't really whether humans will ever leave the solar system. The question is, what form we'll take when we do, how we'll maintain our connection to our origins, and what we'll become as we adapt to life among the stars. The answers to these questions will determine not just the future of human civilization, but the very definition of what it means to be human in an age when the boundaries between biology and technology, between Earth and space, between human and post-human become increasingly blurred. The universe is vast beyond imagination, filled with billions of stars and trillions of worlds waiting to be explored. Whether we reach them as biological humans, digital consciousnesses, or something entirely new remains to be seen, but reach them we will, carrying with us the dreams and aspirations of every human who has ever looked up at the night sky and wondered what lies beyond. The journey to the stars will fundamentally transform not just where humans live, but what humans are. And that transformation is already beginning in laboratories and research facilities around the world, where scientists are quietly rewriting the rules of biology, consciousness, and survival itself. Consider what's happening right now in the field of synthetic biology. Researchers are learning to edit genetic code like software programmers edit computer programs, inserting new capabilities into living organisms with precision that would have seemed magical just decades ago. They're creating bacteria that can survive in conditions that would instantly kill any natural organism. They're designing plants that can extract nutrients from soil compositions that exist nowhere on Earth. They're even experimenting with organisms that can repair radiation damage to their own DNA in real time. These aren't just laboratory curiosities. They're the building blocks of a new kind of life that could thrive in environments where Earth life would perish instantly. Imagine colonists whose modified gut bacteria can digest alien proteins, whose enhanced immune systems can fight off pathogens that have never existed on Earth, whose altered metabolism can extract energy from atmospheric compositions that would poison unmodified humans. But genetic modification is just the beginning. The real revolution involves the convergence of biology and technology into hybrid systems that blur the line between living and artificial. Neural interfaces that can directly connect human brains to computer systems are advancing from crude laboratory prototypes to sophisticated devices that could eventually allow seamless integration between human consciousness and artificial intelligence. Picture an interstellar colonist whose enhanced memory can store the entire technical knowledge needed to build a civilization from scratch, whose augmented intelligence can process information and solve problems at superhuman speeds, whose networked consciousness can share experiences and insights instantly with other colonists, creating a collective intelligence that's far more capable than any individual human mind. These enhanced humans wouldn't just survive on alien worlds. They could thrive there, adapting to conditions and solving problems that would be impossible for unmodified humans to handle. They could serve as the bridge between the biological heritage of Earth and the technological possibilities of an interstellar future. But the most radical transformation might involve abandoning biological existence entirely. Advances in artificial intelligence and computer science are approaching the point where human consciousness might be transferable to digital systems that could survive interstellar travel far more easily than any biological body. The implications are staggering. Digital humans could travel at the speed of light as radio signals, reaching distant star systems in years rather than millennia. They could inhabit robotic bodies designed for specific environments, switching between different physical forms as needed. They could potentially exist for thousands of years without aging, accumulating knowledge and experience on scales impossible for biological humans. Most importantly, they could reproduce by copying themselves, creating populations of digital humans that could establish colonies without the biological constraints of genetic diversity and reproductive cycles. A single digital human could theoretically establish an entire civilization by creating thousands of copies of themselves, each one capable of learning and growing independently. The technology for digital consciousness transfer doesn't exist yet, but the fundamental research is advancing rapidly. Brain scanning techniques are becoming more precise every year. Computer processing power continues to grow exponentially, and our understanding of how consciousness emerges from neural activity is improving dramatically. Some researchers believe that digital consciousness could become possible within the next 50 to 100 years. Others think it might never be achievable, arguing that consciousness involves biological processes that can't be replicated in silicon. But even if digital consciousness proves impossible, other paths to enhanced human survival are opening up. Nanotechnology could potentially rebuild human bodies at the cellular level, creating biological systems that are far more resilient than anything produced by natural evolution. Nanobots in the bloodstream could repair radiation damage, fight off diseases, and even prevent aging by maintaining cellular structures in perfect condition. Advanced life support systems could create protective environments around humans that would allow survival in almost any conditions. Powered exoskeletons could provide protection from crushing gravity or toxic atmospheres while giving wearers superhuman strength and endurance. Neural implants could enhance human intelligence and sensory capabilities, making colonists far more capable of understanding and adapting to alien environments. The boundary between human and machine becomes increasingly meaningless as these technologies converge. Future interstellar colonists might exist as hybrid entities, part biological and part artificial, capable of adapting their forms and capabilities to whatever challenges they encounter. But all of these technological possibilities assume that humans will want to remain recognizably human as we expand across the galaxy. That might not be the case. The pressures of survival on alien worlds could drive evolutionary changes that transform humans into something completely different within just a few generations. High-gravity worlds might produce humans with enhanced bone density and muscle mass, making them giants compared to Earth humans. Low-gravity environments could lead to tall, slender humans adapted for three-dimensional movement in near weightless conditions. Worlds with different atmospheric compositions could drive the evolution of enhanced lung capacity or even completely different respiratory systems. Over time, humans adapted to different worlds could diverge so dramatically that they become separate species, unable to interbreed with Earth humans or with each other. The result could be a galaxy populated by dozens of human-derived species, each adapted to specific types of worlds and conditions. This speciation of humanity raises profound questions about identity and continuity. Would these divergent human species still consider themselves part of the same civilization? Would they cooperate or compete with each other as they encounter one another on different worlds? And would Earth humans still recognize their far future descendants as kin, or would they seem as alien as any extraterrestrial species? The social and political implications become even more complex when you consider the timescales involved. Interstellar civilizations would operate on geological timescales, with individual colonies potentially lasting for millions of years. Governments, cultures, and entire species could rise and fall multiple times before any single interstellar mission reached its destination. The humans who eventually colonize other star systems might be as different from us as we are from single-celled organisms. They might possess capabilities that seem godlike by today's standards, while retaining enough of our essential nature to still carry forward the spark of human consciousness and creativity. But perhaps the most important question isn't what humans will become, but what we'll create. Interstellar colonization isn't just about survival. It's about spreading human consciousness, creativity, and values across the galaxy. The real legacy of interstellar expansion might not be the colonies themselves, but the art, science, and culture they produce. Imagine symphonies composed under alien skies, incorporating sounds and rhythms that could never exist on Earth. Picture architectural marvels designed for different gravity conditions and atmospheric pressures, creating beauty that earthbound humans could never conceive. Consider scientific discoveries made possible by studying alien geology, biology, and physics directly. Each interstellar colony could become a laboratory for human potential, exploring possibilities that are constrained by Earth-specific conditions. The diversity of human experience could explode exponentially as colonies adapt to radically different environments and develop their own unique perspectives on existence. Over millions of years, this expansion could transform human civilization from a single species on one world into a galaxy-spanning network of consciousness that encompasses forms of life and intelligence we can't currently imagine. The children of Earth could eventually become the gardeners of the Milky Way, shepherding the evolution of intelligence and consciousness on thousands of worlds. The technologies needed to make this vision reality are advancing on multiple fronts simultaneously. Private space companies are dramatically reducing the cost of reaching orbit. Robotic missions are revealing the resources available throughout the solar system. Advances in artificial intelligence are creating the autonomous systems that could build and maintain interstellar infrastructure. Most importantly, our understanding of life itself is advancing rapidly. We're learning to create new forms of biology, to enhance human capabilities, and to build systems that can survive and thrive in environments that would be instantly lethal to unmodified Earth life. The timeline for achieving practical interstellar travel remains uncertain, but the fundamental barriers are falling one by one. The physics allows it. The technology is advancing toward making it possible. The destinations are waiting for us among the stars. What's certain is that the first humans to leave the solar system will be embarking on the greatest adventure in the history of our species. They'll be carrying the entire heritage of human civilization with them into the unknown, serving as the seeds of something larger and more magnificent than anything Earth has ever produced. The question isn't whether humans will ever leave the solar system. The question is what will become in the process, and what wonders we'll discover when we finally take our place among the stars as citizens of the galaxy itself. The mathematics of interstellar ambition become even more mind-bending when you realize we're not just talking about sending a few brave explorers into the void. We're talking about potentially relocating entire segments of human civilization across distances so vast that the very concept of home loses all meaning. Because here's the uncomfortable truth that nobody wants to discuss openly. Earth won't be habitable forever. Our sun is slowly getting hotter as it ages, increasing its energy output by about 10% every billion years. In roughly 1 billion years, Earth's oceans will boil away completely, leaving behind a dead, Mars-like world where no form of Earth life could possibly survive. That might seem like an impossibly distant future, but it's actually a relatively short time span in cosmic terms. Entire galaxies have formed and evolved in less time than Earth has left as a habitable world. But we don't even need to wait 1 billion years for existential threats to emerge. Supervolcanic eruptions, asteroid impacts, gamma ray bursts from dying stars, or even human-caused environmental collapse could make Earth uninhabitable within centuries or decades. The geological record shows that mass extinction events occur with disturbing regularity, wiping out most life on Earth every few tens of millions of years. This sobering reality transforms interstellar travel from an exciting adventure into an insurance policy for the survival of human consciousness itself. We're not just exploring because we're curious, though curiosity certainly drives us. We're exploring because staying confined to a single world is ultimately a death sentence for our entire species. The urgency of this situation is driving some of the most ambitious engineering projects ever conceived. The concept of generation ships, massive spacecraft designed to carry entire communities across interstellar space, is moving from science fiction into serious engineering studies. These wouldn't be cramped capsules like the spacecraft that took us to the moon. They would be rotating habitats kilometers across, containing entire ecosystems and supporting populations of thousands or tens of thousands of people. Picture a giant wheel spinning slowly through the darkness between stars, its rotation creating artificial gravity that feels nearly identical to Earth's pull. Inside, forests and rivers and cities exist under artificial skies that could simulate any Earth environment from tropical beaches to snow-covered mountains. Children would be born, live their entire lives, and die of old age while the ship continues its journey across the galactic void. The engineering challenges of building such structures push every material science and life support technology to its absolute limits. The hull would need to be strong enough to contain an entire atmosphere while protecting against micrometeorite impacts and cosmic radiation for centuries. The artificial ecosystems would need to maintain perfect balance without any external inputs, recycling every atom of carbon, nitrogen, and phosphorus in closed loops that could operate flawlessly for hundreds of years. But perhaps the most daunting challenge involves maintaining human society and culture across multiple generations of interstellar travel. How do you prevent social collapse when people are born into a confined environment they can never leave? How do you maintain motivation and purpose when the original mission goals become abstract concepts that no living person has experienced directly? The psychological pressures would be unlike anything humans have ever faced. Imagine growing up knowing that you'll spend your entire life traveling toward a destination you'll never see, working to maintain systems and traditions for people who won't be born until after you're dead. The temptation to abandon the mission, to turn the ship around, or simply to give up entirely could become overwhelming as generations pass and the original Earth becomes nothing more than a story told by elders. Some researchers propose that successful generation ships might need to be essentially totalitarian societies where individual choice is subordinated to mission success. Others suggest that advanced virtual reality could allow people to experience unlimited variety in simulated environments, preventing the claustrophobia and despair that would otherwise doom long-duration missions. But there's another approach that sidesteps many of these problems entirely. Instead of sending massive generation ships carrying thousands of people, we might send much smaller crews in advanced life support systems designed to keep humans alive for extended periods without requiring full-scale ecosystems. Medical advances in life extension could potentially allow individual humans to survive interstellar journeys that would normally require multiple generations. If aging could be slowed or stopped entirely, a crew that begins an interstellar journey could still be alive when it reaches its destination decades or centuries later. They would arrive with their memories of Earth intact, their skills and knowledge preserved, their original mission motivation still burning bright. Research into cellular regeneration and genetic repair mechanisms is advancing rapidly. Scientists are identifying the biological processes that cause aging and developing techniques to slow or reverse them. Some organisms on Earth already possess near immortality, regenerating their cells indefinitely without the gradual breakdown that kills most living things. If these biological processes could be understood and replicated in humans, interstellar travel could become as simple as taking a very long trip rather than embarking on a multi-generational odyssey. The crew would enter suspended animation during the journey, aging slowly or not at all, then wake up at their destination ready to begin the work of establishing a new human settlement. The technology for reliable suspended animation remains elusive, but the fundamental research is making steady progress. Medical techniques for inducing hypothermia in trauma patients are becoming more sophisticated. Animal studies are revealing how some species survive months of near-freezing temperatures without cellular damage, and advances in nanotechnology could potentially create systems that maintain and repair human bodies at the molecular level during extended periods of suspended animation. But even if we solve the technical problems of keeping humans alive during interstellar journeys, we still face the monumental challenge of what to do when we arrive at our destinations. Because the reality is that most potentially habitable worlds will be hostile to Earth life in ways that could kill colonists within hours or days of landing. Atmospheric compositions that are toxic to human lungs, gravity so strong it would crush Earth-adapted bones and organs, radiation levels that would cause fatal cancer within weeks, microbial life forms that could trigger immune responses unlike anything our bodies have evolved to handle. The list of potential hazards is endless and terrifying. This is where robotics and artificial intelligence become absolutely crucial to human interstellar expansion. Instead of sending humans directly to alien worlds, we need to send robotic precursor missions that can spend decades or centuries preparing environments for human habitation. Advanced manufacturing robots could extract resources from alien soil and atmosphere to construct pressurized habitats, life support systems, and even breathable atmospheres inside enclosed spaces. They could analyze local biology to identify potential threats and develop countermeasures. They could even begin terraforming processes that would slowly transform entire planetary environments to become more Earth-like. By the time human colonists arrive, they could find fully prepared settlements waiting for them, complete with protected environments that feel almost like home. This approach dramatically reduces the risks of interstellar colonization while maximizing the chances of successful settlement. But the most revolutionary possibility involves not sending traditional humans at all. The convergence of artificial intelligence, genetic engineering, and advanced robotics is creating possibilities for hybrid entities that could thrive in alien environments while retaining essential human consciousness and creativity. Picture colonists whose enhanced physiology can survive in low pressure, high radiation environments, whose modified metabolism can extract nutrition from alien biochemistry, whose augmented intelligence can solve problems and adapt to challenges that would overwhelm unmodified humans. These wouldn't be robots or artificial beings, but enhanced humans specifically designed for life among the stars. The ethical questions raised by such modifications are profound and disturbing. Would genetically enhanced interstellar colonists still be human in any meaningful sense? Would they have the same rights and moral status as unmodified humans? And what happens when enhanced and unmodified populations encounter each other after centuries of separate development? So here we are, standing at the edge of the greatest transformation in human history. Will humans ever leave the solar system? The answer isn't just yes, it's inevitable. The physics allows it. The technology is racing toward making it possible, and the universe itself is giving us no choice but to reach for the stars or face extinction on a dead world. The first humans to make that journey will be carrying something far more precious than just their own lives. They'll be carrying the entire story of our species, every dream, every discovery, every moment of human consciousness into the infinite dark. And when they finally arrive at those distant worlds, they won't just be explorers anymore. They'll be the seeds of something we can barely imagine. The future of human civilization doesn't end at the edge of our solar system. It begins there,